Okay, so I'll skip the usual things. I know most of you, and most of you know me. If you don't, just approach me in the lobby, and we can chat about something. Now, if you remember, 2 years ago, I felt really old and wise, and I had a keynote on progressive or prog C++, inspired by my advanced stage, and it was meant to be a wise and profound talk that you should all watch if you haven't. And unlike that one, the talk today is going to be quite different. Now, I'm no longer wise. I'm no longer old. Now I'm back in my teenage years, and I'm rebellious. Some of the people know why. So I'm now in a rebellious state, and instead of giving you good advice, I decided to go against the establishment, against the man. So this time it's punk rock C++. So we are against everything good. We are out of our minds, right? Because we are teens and we don't want to listen to the elders. And the first thing that I decided to do that was completely out of my mind is the following. Obviously, the usual, the code in this presentation is slideware. The chunks written by AI, and large chunks written by AI, which is the first time that I used AI for coding, so it must be good. And obviously, this was before Friend's keynote, and now I know better. But just to appease her, you should know that I planted a few trees. So for all the electricity and the environment impact that my queries to the AI had, I did do my part and I planted a few trees. So remember, do not use this in production. Not only because it's AI, because it's bad advice, right? Okay. So let's start with the first act of teenage rebellion. In the next room, we have Peter, or not next room, but down below. And he's our C++ Misra guy. And I love Peter, but whenever I see rules, they need to be broken. So there is a rule on recursion in Misra that functions should not call themselves, either directly or indirectly, because obviously you can crash your stack, right? And I'm not a fan of recursion. I might be known as a functional programming guy in C++, but I still don't like recursion even. But when I see a rule like this, you need to write recursion. You need to rebel against the guy or the man, right? But I wanted to do it in a smarter way, not just to rebel for the sake of rebellion, but to actually invest some time into reading the reason why we shouldn't use recursion. Okay, recursive functions use some space on the stack, and it goes up. But what if we can make recursion without using the stack? It would subvert the rule, so it's not totally punk. It will still be legal, but we are going to go against the rule, but without breaking any rules. If that makes any sense, which it doesn't, but that's punk. So then we go to DuckDuckGo because we don't like any other search providers, and we say C++ stackless. Let's see what it gives us, and it says, okay, stackless coroutines in C++. Stackless coroutines in C++. So coroutines in C++ are stackless. If we write recursion so that it uses coroutines, then we should be safe. So we have something called co-recursion, which we'll later see what it is. Then we have the ugliest and the worst implementation of Fibonacci, because obviously you need to implement Fibonacci any time that you talk about recursion. And for each of the recursive calls, we tell the compiler this is a recursive call using some strange keyword called coawait, but just ignore the name of the keyword. This is call my recursive function operator. Okay? So we should be fine. Stackless coroutines in C++ are stackless, right? as it usually goes in C++, no. So there are situations where stackless coroutines are not stackless. The compiler can optimize your code and elide the heap allocation. And obviously, this is one of the rare abbreviations in C++ that kind of sounds nice, Halo. Obviously, the heap allocation illusion optimization is an okay-ish thing, but obviously this abbreviation is a little bit of a fake just so that it sounds nice and saintly. So if we didn't have this optimization, then nobody would use generators. Because if you just want to iterate and sum numbers from 1 to 10, you really don't want any heap allocation to happen. So in most situations, when you write your own coroutines, you would love it for the compiler to perform this optimization. In our case, because we are punk, we want to disable the optimizations as much as we can, because we cannot allow anything to end up on the stack. Because again, Stack Overflow. The sure way to disable Halo is to define the new and delete operators on your promise types, even if they're using the default global new and delete, or you have some memory pools or something, it effectively disables the Halo. So we should be fine now, right? If we created coroutines, stackless coroutines, and disable the thing that doesn't make them stackless, then we should be fine. Nope. So still, the coroutine part, the suspended and after suspension part will end up on heap, but it doesn't mean that the whole function ends up on the heap. For that, we need to tell the compiler, as soon as you get into a coroutine, you need to suspend it. So not a single part of the coroutine can be a normal C++ function. And we say it by saying that we suspend always on initial suspend. Not really intuitive as the naming is, but yeah. And we also, in order to collect the result and to be notified when the coroutine ends, we are going also to suspend on when somebody wants to exit the coroutine. But this is still not everything that you need to do. The last thing to tell the compiler that we really don't have any, let's say, non-suspended part of our coroutines is to say that we are never ready. So when the compiler tries to execute the coroutine, we say, no, we don't have the result. And then it gets suspended. So now, really, all the things that we've done so far is just to forbid every single part of the coroutine to end up on the stack, which is cool. Now, obviously, this is punk C++. You should not do this. But at least you've learned, if you want the optimizations, you learned not to do this, just to do the inverse of what I said. But again, this is punk C++. And we have a couple of things more to implement. We need to implement await resume, which will return the result. And we need to implement the await suspend. So, as I've said, so far, the only thing that we've done is to define our coroutine computations, the recursive computations, and we didn't execute anything. We forbade C++ to execute a single line of code in any of our coroutines. Fine? So if we forbade C++ to execute it, who is going to execute it? We need to write a way and to implement our own execution, our own virtual machine that is going to evaluate these recursive functions. In order to do that, we'll need some state. We'll need to create something that I'll call here a recursion context. You can consider it execution context or the virtual machine state. It will need to save the result. It will need to have a space to save the result of the computations. And it will need to have a stack. Now, why do we need a stack? We still need to simulate the same execution model that C++ has, just not on the stack, but in the stack. Does this sound sane? Obviously not. So I used to teach at a university, and one year they gave me young students to work with, which was a mistake. And one of the really big problems that they all had is to differentiate between the chapter called the stack and the chapter called the stack, just in the different part of the book, because one was the function stack and the other was the structure stack. And now just imagine them listening after, I don't know how many hours I had to spend to force them to differentiate between those things. Now just imagine if they watched this talk where I'm implementing the function stack with the structure stack. They would say, it was all a lie. But again, this is punk C++. So we are going to need, for each of the functions that got suspended because there was a recursive call, we'll need to save its stack frame or coroutine frame somewhere. So let's put it inside of this. So this will contain all the handles to the coroutines that we need to resume. So when somebody calls coreturn, then promise type return value will be called. That function will store the result inside of the recursion context result. And when somebody calls await resume, then that stored result will be passed to the caller. When we want to suspend the coroutine, the thing that we need to do, the main thing, is to propagate the context between all the nested recursion calls. So all the calls inside of the single recursion need to have this shared virtual machine state and know about the virtual machine state. And that's the line where we connect recursion context to the promise recursion context. And the next thing is, obviously, just as the compiler would do for normal functions, we push the current suspended coroutine onto the stack. And the last part, we need to implement the logic of the virtual machine. Again, we are just re-implementing what normal functions in C++ do. We are creating the context for all of the recursion, so including the stack for the handles. And we add the first call for the recursive function to the top of the stack. Until stack is empty, we take whatever is on the top. We check, is it done? If it's done, we destroy the handle and remove it from the stack. The same thing that the compiler would do anyhow for normal functions. And if it's not done, then we again connect the context and we say, okay, you can resume this function. And this iterates until the stack is empty, which means that all the recursive calls, however many there were, they have ended, and we have the proper result inside of the context, the recursion context object. Cool? So I did use, for this part, I didn't use AI, but for some of the later things I did. But one of the things that I promised when I was announcing this talk on social media is that I'm not going to ask ChatGPT to give me the definition of a coroutine. So I need to give you a definition of coroutines, right, at some point. It's weird that I skipped a few slides before doing that, but now we know what coroutines are. Coroutines are a mechanism to redefine how parts of the C++ abstract machine works. Obviously not, but we did that in the previous example. We created our own expressions that define recursion or whatever, and we created a virtual machine where we control how we are calling the functions. The only thing, obviously, we simulated the same thing that the compiler does for normal functions, but we could have done whatever we wanted. Okay? Now, the recursion part, obviously, I said that the reason why we wrote it is that we wanted to be against Misra, but we actually had experiments with deep recursion and stuff, so this code was kind of a product of something more serious than what I'm pretending it to be. But most of you are not going to care about deep recursion because you don't work with, I don't know, you're not writing virtual machines for other programming languages which love recursion. But if you forget about the optimization and disabling the halo from the previous slides, you could have noticed that as we control when a function is called, we also have a notification when a function ends. We have a notification when the function tries to call return. We have a notification when a function is suspended. You can log all those elements, all those events. So you could create, let's say, a singleton logger. Again, we are punks, so singletons are fine. You could have a function called increase indent and decrease indent. When you want to call a coroutine, you say increase indent. When you want to exit a coroutine, you say decrease indent. And from inside of the coroutines, you call print. And then you have properly indented logging output depending on how deep the stack trace at that point was. So you could see, okay, this output is from a function that was called by this output, etc., which can be quite useful. Apart from this, you can add whatever you want into the recursion context, or you would call it execution context. You could create either a global context for the whole chain of calls, or you could even use these events. I'm calling a function, I'm returning from a function to allocate new stuff, new shadow contextual information for each of the function calls. Okay? So now we can properly define what coroutines are. Coroutines are a mechanism to hook into function call events and provide shadow contextual data. Okay. So now we can move to something that I often mentioned in my previous talks in various reasons, but I never delved into the implementation. But this is something that I'm really fond of, and I'm not the only person who thinks it's a good idea, even if the powers that be in the C++ committee don't. If you want more details, then I'll go here. Obviously, watch some of my previous talks or read Antoine's blog post on abusing co-await for the thing that I'm just going to show. So one of my really, did you take the picture? Okay. So again, you know a part of my background, functional stuff, etc. And you might learn by now that I don't really like exceptions for various reasons that I'm not going to go into. And that sentiment is shared by a lot of people, so we got std expected in the standard. The idea of std expected is, okay, you don't want some magic mechanism to deal with your errors. You want it to be explicit to say, my function can return a value or it can return an error. And you can have several of those functions because just like with exceptions, every function could throw an exception. In this case, all the functions that we've defined could return an error. Now, if you want to connect all of these, in the standard, std expected has dot and then, and it has dot transform. So you would be able to implement the generate email link function just by chaining saying get input and then parse email dot transform format link. And it would do something similar to this. But obviously, this smells of functional programming, and we are punk C++, so we don't want to use functional programming. We are going to write it in an imperative way by calling a function, storing the result, calling a function, storing the result. How you should read this code, again, the keyword co-await might be a misnomer, a really bad name, so we are going to pronounce it a little bit differently in this example. It will be get value if it exists from get input, and store it inside of the variable called input. Okay? The next coawait is again, get a value if it exists from the result of parse email input and put it into email. And then do something with that email. Readable code if you just ignore that coawait doesn't mean a thing in this context. Now the question is how to implement something like this. Here we don't really need to have a complex context for our recursion or whatever. We can just have a pointer to, in this case, co-expected, because we cannot really do this for the standard class, unfortunately. I did try, and I had promises that it should be possible, but at least not with current compilers. The getReturn object is the normal function from the, let's say, coroutine interface, which returns the return object, right? And in this case, we will say we never want to suspend. Here we are not trying to disable any optimization. We are not really using coroutines, so we don't really need to suspend as soon as we get into the coroutine, and we don't need to suspend when we get out of the coroutine. Now, if we did suspend when we get out of the coroutine, it would be easier and safer to deal with the result. But this code was generated by AI, so you should try to find issues in it. Not in this slide, but in the following slides. And then return value, obviously, collects the value that needs to be returned. And unhandled exception will be called if there is an exception inside of your coroutine. In this implementation, I said ... I would say freely put std terminate here, because if you're using expected, you don't want to use exceptions as well. You shouldn't mix and match different error mechanisms inside of the same function, again, unless if you're punk. Okay, so for getReturn object, we allocate the result object. Then we take the pointer to it and put it into the context, the result pointer that we saw a bit earlier in promise expected, and we return the result. Now, obviously, I said you should try hard to find the issues in the following code. And I forgot to remove the 3 exclamation points in this slide. So, does anybody have anything against this AI-generated code? No? Okay, so Danny said everything is fine. Obviously, I didn't put the everything is burning, this is just fine meme here. Who thinks that this will crash? So, surprisingly enough, this works. This is undefined behavior, but this works. Again, undefined behavior, but it works. Do you have any idea why?
Because of our stack.
So, usually when you see something like this and it works, it means that the memory just wasn't zeroed out or something like that, so it's using the space that was previously occupied by a variable. But it's not the case here. This works. It relies on something that is not, that every compiler does, but it's not required of every compiler to do it in this particular case. And that's the return value. Yeah, return value optimization. So the result variable is not located in the stack of this call, but in the caller. So when you take the address of it, you're getting the result of the variable in the caller and not of your local one, because they're the same thing. And this is so cool, obviously. So again, just imagine any of my students where I gave zeros for this, and the compiler just does the thing that makes this work. It will be completely insane. So obviously you should not do this, but it works. If the compiler decides not to perform RVO, then obviously this will going to be a proper UB. And this is undetectable UB. Again, don't write the code like this. This is AI. And don't use AI, like Fran said, not only because of the environmental reasons, but also because you get code like this that works. Okay, so when somebody wants to return a value, so they say co-return, we just store the value, right? That part should be trivial. Now, the only reason to suspend the coroutine, if the expected has a value, then just continues normal. If it doesn't have a value, then we say, okay, we are a coroutine all of a sudden, and we want to stop. Okay, sure. And then you say, await ready is if expected has value. So again, if we have a value, then everything will proceed as normal. If we don't have a value, then the coroutine will suspend. Resuming is not that important. The important thing is await suspend. What we want here to happen, we are in await suspend because expected contains an error. This means that as a result, we just want to pass on that error and do absolutely nothing else. We don't want to continue executing the function because an error happened. Everything else needs to be forgotten. Okay? And this is what we are doing here. We are storing inside of the value where we say, okay, it's std expected of our current error, and we just destroy the handle without ever continuing, without ever calling it. So whatever was after suspension, we just say, okay, nope, ignore it. Cool? And obviously, if you really want to be punk, now that you know that anything that can look like expected or an optional, you can wrap it inside of a coroutine. And if you have a lot of code in your project with early returns, if this pointer is null, return. If this pointer is null, return. If dynamic cast failed, return. And you really don't like writing ifs, then you can just create a codynamic cast, which will be a coroutine implemented in the same way like expected. If dynamic cast returns a null, just exit. If it doesn't return a null, auto star object is going to be an instance of the subclass, a valid instance of the subclass so that you can work properly with it. So you might remember that I didn't define recursion, that I didn't define coroutines some time ago, and I'm not going to do it. I'm going to move to one of the maybe most lovely examples in this presentation. You probably know that I'm a big fan of std variant, but not for the reasons that, for example, Klaus showed in the previous presentation. Variant is often used for a bag of different types, so that you can create JSON documents, so that you can create shape that can be circle or something else. For me, variants are meant to be the best safety feature in C++. And again, this is punk C++, but I can still say something sane during this presentation, right? So what you should do with variants, if you have a complex application which usually has a lot of state inside, but your application usually can be split into several different completely separate states, like in a web browser, connecting to a web service, reading from the web service, showing the page. When you're showing the page, obviously, just forget I said web browser is something that reads documents from the website. when you're showing the web page, you no longer need the socket. What you usually do is, okay, when I finish reading, I say .close. You kind of avoid RII. You're doing essentially deinitialization manually because you put everything inside of your class. If you split this into several states, in several classes, one class for we are connected, and one class we are showing a document, as soon as you switch the variant from one type to the other, the destructor of the previous one executes, and everything is deinitialized that you no longer need to use. Now, I'm not going to have an example that sounds sane, because I tried to make it a little bit more zen. So this is a breathing exercise. For breathing, we have 4 different states. We have inhaling. Then we have meditation while we have inhaled. Then we have exhaling, and then we have rest. And all of these are different states that we need to switch through. So using state covariant of all of these. As soon as we switch to, I don't know, exhaling state, we no longer have the seconds stillness stored anywhere. Again, if it was a socket, it would be destructed. If it was a unique pointer, it would be freed, etc. The issue with code like this is that whenever we want to switch state or update states, we need to say std get if to get a pointer to that. If it's null, and you kind of see where I'm going with this. So if it's null, you want an early return. But the difference between this example and the previous ones is that in the previous ones, we had a single happy path. So coawait always knew what to aim for. We don't usually want to transform the error state. We don't want usually to do anything with the error state just to propagate it. In this case, we have several happy states that we want to deal with. So we can't really just say coawait on the state. We need to tell the coroutine which type of the state we expect in which function. So if we want to update the inhale state, we could just start by saying coawait, and then a magic function called coget inhale t of state. Okay? If inhale is not our current state, we're just going to exit and leave state unchanged. If we are in inhale state, then we're going to increase the depth of our inhale, because it always increases, right? And we return the new updated version. And if you listened to Juanpe's talk or any of his previous ones, this can also work perfectly with immutable data structures. Because you're generating a new value and returning the new state if you needed to update it. Okay? The same if you want to switch from one state to the other. Again, you say coawait, coget, blah, blah, blah. You might use something from that result to generate the new state. In this case, we're just switching to a peak of 12 for some reason, and we're returning the new state. So we have created a state machine with a really nice syntax. For each of the function, we have a guard on top. This function works only with this state, and it returns either the same state or the new one. Okay, for the update as well. And then we could just compose these functions like any other, and you get a whole breathing cycle just by composing these 4 functions. And you would be able to call this function in a loop, and then obviously you're alive because you're breathing and you're meditating and you're thinking about life and things. Now for this, I'm not going to show the implementation. If you want to see really well documented again by AI, but this implementation actually doesn't have UB as far as I've seen. It's just more involved than the previous one and more nicely written. It took me several restarts to force the AI to do actually do what I wanted it to do. So it would be much faster if I did it by hand, but at least I planted a few trees. So the new definition of coroutines, because if you remember, I didn't define coroutines at the beginning of the talk. Coroutines are the most complex control flow structure in C++ that somehow turned out to be useful as for asynchrony and lazy evaluation. And I mentioned lazy evaluation here. The only reason for it is because we got STD generator. If we didn't get that, nobody would even think that coroutines are for anything apart from asynchronous computation. So another definition. Everybody agrees with this one? Okay. And it's one of the rare control flow structures in C++ that hides curly brackets. So if you notice, with early returns, we had at least scopes, even you should write curly brackets after ifs. Here, no. So hidden curly brackets, awesome. If you have any C friends or Zig friends, show them this, because they don't even like the destructors to be called magically, while they don't really realize that destructors are called. Show them coroutines, they will love you. Okay, so let's come closer to the end. Apart from this, coroutines can be used for creating parsers. Just like we've defined the recursive definition of a function and then created an abstract machine that runs it. There is a library called Parsco by somebody that I don't know the proper name of. The user is called No More Secrets, which is cool, but his or her or name is a secret, so I have no idea. But it's a really interesting idea for the library where you can define parsers just by combining different, let's say, parser matchers. So you would be able to define, I have a matcher called keyword, and maybe a specific keyword like call8, and then match a function call afterwards, and then you define a grammar with coroutines, and then it magically parses the thing that you wanted to parse, right? And the last thing that a proper sane library by a friend from KDE called Dan Vratil, where coroutines are actually used for the thing that they were meant for. So if you use Qt and you have asynchronous computation, asynchronous tasks in Qt, including signals, slots, and everything else, this is the library that you need to check. It's called QCoro. And it implements exactly what you would expect the standard to have already implemented in the standard, just for the Q things. Okay. So the last one, the last definition, because if you remember, I didn't define coroutines at the beginning. Coroutines are a way to chain weird kinds of functions in C++. Or not even functions, weird kind of things in C++. So these are the definitions for coroutines. Coroutines are functions that can be suspended and resumed. Coroutines are functions on a custom abstract machine. They're a way to register hooks for function invocation. They're the most complex but coolest control flow structure in C++. They're obviously state machines, either with variant or with the virtual machine that we created for the recursion. They're also parser combinators, and I had to put the word monads because I haven't done so in a while in any of my talks. And if people had followed my meeting C++, let's say, progression over the years, this is a hint to the first of my talks, which was called monads in chains. So not monads of chains, but close enough. The last thing that I want to say is that Manning has some bundle with Fran's books, Anthony's books, and mine book, and a couple of others that I know nothing about. If you want to save money while buying books. If you're in that sort of thing, you can just check it out and buy books. Okay, and this is the usual last slide. If you want to contact me through my company or personally, you can use these things. Thank you. Your punks. Nobody.
And no questions from the online
Oh, that's so. Well, that's punk, but that's depressing. Okay, that should be it then. See you in the hallway if you want, right?